This lesson covers the OpenGL graphics pipeline, a sequence of states through which your objects are processed for rendering to the screen. This will not be an exhaustive tour of the pipeline, but a practical overview with emphasis on the aspects that are most important for these introductory lessons. This is a simplified view of the OpenGL 4.4 pipeline. Processing begins in the vertex fetching stage. This is where data enters the pipeline. This stage, and the others colored in blue, are not programmable. You won't provide shaders for these stages. You can program the vertex shader, tessellation, geometry shader, and fragment shader stages, and you configure the non-programmable fixed function stages. Vertex fetching is the beginning of the pipeline. So what exactly is a vertex? A vertex is, at least, a position in 3D space. When considering a line, there are two vertices that mark the endpoints of the line. 3 vertices for a triangle, but I say at least, that's at least a position because it's often much more than that. Vertex might contain a color, a normal, useful for lighting calculations, texture coordinates, and more. This data is sent to the vertex fetching stage using OpenGL buffer objects, and the vertex fetching stage is invoked with OpenGL draw calls. When you supply vertex data to the pipeline, you must specify the topology of that data. That is to say, how those vertices should be interpreted. OpenGL supports a number of primitive data types. You've seen one already, GL points, which indicates that the data coming through the pipeline is organized as the list of individual vertices. OpenGL also supports a list of lines and triangles, where each pair or triplet of vertices constitutes a line or triangle respectively. Lines can be made into loops, and triangles can be described as strips or fans and include adjacency data, but those are just alternate ways to describe how lines and triangles are formed from a set of vertices. The most basic primitive types, and what we'll use most, are simple lists of points, lines, and triangles. OpenGL also supports patches, which are surfaces described by a number of control points. A triangle is a patch with 3 control points, and a quadrilateral has 4 points. Patches with more than 4 control points refer to surfaces constructed from Bezier curves, and patches are used for tessellation, which we'll discuss after a bit. The vertex shader is the first programmable stage in the pipeline. Remember from our point demo that shaders are just small programs that execute on the GPU, the graphics processing unit. Vertex shaders execute on each vertex received by the vertex fetching stage, and typically, at a minimum, modify the vertex position and pass the position to the next stage through the GL position variable that you've already seen. Your applications will contain any number of vertex shaders, though only one can be active at any time. Tessellation is the next stage in the pipeline and is actually 3 stages. 2 programmable stages surrounding a fixed function stage. Tessellation is optional, and its job is to subdivide geometry. This is a very powerful feature of modern OpenGL, which allows low poly models to be transmitted to the GPU without sacrificing the quality of high poly rendering. Consider the following example. Here, an icosahedron is subdivided to build a sphere. As the subdivision increases, the facets of the sphere are less pronounced, but the very same low poly model is submitted to the pipeline. The new triangles that make up the sphere are entirely generated on the GPU. This allows for dynamic levels of detail where models that are close to the camera are highly subdivided, while objects that are farther away would not benefit from high-resolution rendering are not subdivided at all. The next stage of the pipeline is the geometry shader, and like the tessellation stages, the geometry stage is optional. While the vertex shader operates on individual vertices, the geometry shader processes entire primitives. It can add and remove geometry from the pipeline, and even redefine the topology of primitives. A common application of geometry shaders is point sprite expansion. A point sprite allows a texture quad or other shape to be rendered while specifying just a single vertex, a point. The point represents the center of the quad, and the geometry shader constructs the 4 surrounding vertices to form the quad. Point sprites can be used for things like billboarded textures, textures that always face the camera, and for particle effects. The next stage in the pipeline is rasterization. The rasterizer is a fixed function stage which determines what fragments to attempt to render for a primitive. A fragment is a potential pixel that can still be rejected before being written to the frame buffer. Generated fragments are passed to the fragment shader stage along with interpolated vertex data. Since this is our first mention of interpolation, let's spend a little time describing the process. Consider a triangle that enters the rasterization stage. It's made up of 3 vertices which contain at least a position, possibly data like color, surface normals, and texture coordinates. The rasterizer produces the individual fragments that make up that triangle. Each fragment has its own position, color, surface, normal, etc. It's derived from the original 3 vertices. Consider the following example, which is the output from the next demonstration application. Here, the 3 vertices are provided with the colors red, green, and blue, respectively. Notice how the pixels within the triangles are variations of these colors, weighted by the distance from each of the points. This is a visual explanation of what's happening in the interpolation process. Just as the vertex shader executes on each vertex, the fragment shader executes on each fragment that's output from the rasterization stage. Its job is to output a color and/or a depth value. As demonstrated in the last lesson, colors are represented with 4 8-bit channels, red, green, blue, and alpha, where the alpha channel indicates the opacity of the color. Each channel has values between the range 0 and 1. All zeros for the RGB channels produce the color black and all ones white. The depth value is the distance between the fragment and the camera within the range 0 to 1, where 0 is the nearest value and 1 the farthest. The vertex shader is often the most costly stage in the pipeline, and not simply because of the number of instructions that might be employed, but because there are typically so many fragments as compared to vertices. For example, if a single triangle occupies the entire screen, the vertex shader will execute just 3 times, but the fragment shader executes for the combined resolution of the screen. A 1920 by 1080 resolution will yield 2,073,600 fragments. The fragment shader executes for every one of those fragments. The last stage in the pipeline performs per fragment operations and might write fragments to the frame buffer. The frame buffer is typically just a 2D texture and matches the resolution of the application in what's ultimately presented to the screen. The default frame buffer is also called the back buffer when describing a multi-buffer or swap chain, and is usually provided by the windowing system, GLFW so far in our examples. However, you can also create additional frame buffers that are disconnected from the display. Such frame buffers allow for off-screen rendering and post-processing effects. In fact, there are separate buffers for fragment colors, the color buffer, which we've already mentioned, and the depth buffer. And multiple buffers can be bound to the pipeline for simultaneously writing numerous pieces of information. I said that the per fragment shader might write fragments to the frame buffer because this stage optionally performs a series of culling tests. By default, and when enabled, the depth test, or Z-test, checks to see if there is already a pixel in the frame buffer that's closer to the camera than the fragment in question. If so, the current fragment is discarded because it would be hidden behind the previously written pixel. This process is known as Z-culling, and it requires that we clear the depth buffer to the value 1, where 1 is the farthest value away from the camera. We have to do that for each iteration of the game loop. Moreover, if we sort our opaque objects from front to back before we send them to the pipeline for rendering, then we would write the nearest pixels and call out all the remaining pixels at the same positions. Another culling test is the stencil test, which can be likened to physically drawing on a cardboard or plastic stencil. Only the writable pixels defined by the stencil will have their values modified. If the fragment isn't called, it's sent to the color blending operation, where its value is combined with whatever color is already present in the frame buffer. This is commonly used for semi-transparent fragments, whose color is determined at least in part by whatever is behind them. We'll cover color blending in more detail in Lesson 6. That's the end of this short trip through the OpenGL graphics pipeline. Again, this hasn't been an exhaustive discussion, but touches on the broad strokes of the pipeline. Throughout these lessons, we'll be focused on writing vertex and fragment shaders, though we will discuss tessellation shaders and compute shaders. That's a stage which stands independent of all the other pipeline stages, and more complex rendering in Lesson 6. In the next lesson, we'll explore the mathematics behind 3D graphics.